the intermediate value theorem, or sometimes called the IVT. So it states that if function f is continuous on the closed interval ab, where f of a is not equal to f of b, and if n is any number between f of a and f of b, then there exists at least one number c in ab such that f of c is equal to n. To visualize this, let us look at this graph. See that n is between f of a and f of b. Also, a is less than c and c is less than b. So therefore, we know that there is a possibility that f of c is equal to n. Now let me try to explain the theorem as informal as possible. There are 2 points a and b, and these 2 points are connected by a continuous function. Now imagine a straight horizontal line called n that is in between the 2 points. See that horizontal line will always intersect the curve, and the intersection will create a point. Let's call it the intersection of c and n, and it is a point in the function, so we know that f of c is equal to n. Notice how a is less than c and c is less than b, and f of a is less than n and n is less than f of b. So this is always the case. So the intermediate value theorem says that as long as the function is continuous, then there is also at least a number c such that a is less than c and c is less than b, and f of c is equal to n. This theorem also states that at least one value c, which means that we could have more values of c. So these 3 figures below shows a graph of functions from continuous function and discontinuous function with IVT. So in figure A, this is a continuous function where IVT holds for a single value of c. And in B, a discontinuous function where IVT fails to hold. And in C, it is a continuous function where IVT holds for a multiple values in its interval AV. For example, the polynomial function f of x equals x squared minus x minus 5 is continuous on the interval -1 and 4. Use the IVT to find the value of c given that n is equals to 1. Since a is equals to -1 and b is equals to 4, by substitution we get f of a equals -3 and f of b equals to 7. Since we already have the value of n, which is 1, we now proceed to finding the value of c. We substitute the variable c to the variable x to the function and equate it by the value of n. So now we have c squared minus c minus 5 equals 1. And by subtracting -1 to both sides, we get c squared minus c minus 6 equals 0. So, by factoring, we get quantity of c minus 3 times quantity of c plus 2 equals 0. And now, we have the solutions. We can notice that there are 2 solutions for c in this problem. However, despite the latter equation has 2 solutions, only the value of c equals 3 is between the interval of -1 and 4. There is also a corollary to IVT that states if f satisfies the hypothesis of IVT and f of a and f of b have opposite algebraic signs, then there exists a number x between a and b for which f of x is equal to 0. This means that there's some number between f of a and f of b when they have opposite signs, which is 0, and the x value that corresponds that y value of 0 is called c, which is also the somewhere between point A and b. This fact is often used in locating real zeros of a continuous function f. If f of a and f of b have an opposite signs, then by identifying n equals 0, we can say that there is at least one number c in ab for which f of c is equal to 0. In other words, if either f of a is greater than 0 and f of b is less than 0, or vice versa, then f of x has at least one 0c in the interval of a b. These 2 figures shows a function when locating zeros of functions using the intermediate value theorem. In A, there is only one 0c in the interval, while in B, there are 3 zeros c sub 1, c sub 2, and c sub 3 in an interval of A and B. Note that this theorem will be used to prove the existence of solutions but will not actually solve the equations. And this applies to continuous functions and is used to prove that equations, both algebraic and transcendental, are solvable.
Bisection method. As a direct consequence of the intermediate value theorem, we can devise a means of approximating the zero of a continuous function to any degree of occurrency. Suppose y is equal f of x is continuous in the closed interval ab such that f of a and f of b has opposite algebraic sign. So, kanang bisection method kay pareha ra gyud na siya sa IVT. Ang kalaihan lang sa bisection kay na siya condition nga ang f of a and f of b has opposite signs. Bali positive ang usa, then negative ang usa. Nya di ba kung opposite siya og sign, then ang pasabot-an na kanay function nga equal to 0 sa tunga. Kay tungod ang 0 naaman within the interval of positive and negative. So gikan na concept, ang bisection method kay pagamiton para mahibaw-an nato kung unsa ang pinaka-approximate value of x na kung i-substitute nato sa given function kay mo approximate equate sa siya sa 0. Nya tungod kay dili man nato maingon dayon nga ang 1 kay mao gyud na ang value or sa x or ang 2.5 kay mao gyud. So mao nang gikinahanglan ang bisection method. Bisection method is done by finding the midpoint of the given interval and doing the same in a succeeding process. Suppose we bisect the interval AB by finding its midpoint, m sub 1, which can be determined by dividing the sum of a plus b divided by 2. If function of m sub 1 is equal to 0, then m sub 1 is the zero of the function and we proceed no further. Dira lang na lang tataman kay nakuha naman ang 0. But if ang function of f sub 1 is not equal to 0, we can say that if f of a and f of m sub 1 have opposite algebraic sign, then f has a 0 c and a and m sub 1. If f of m sub 1 and f of b have opposite algebraic sign, then f has a 0 c in n sub 1 and b. That is, if the function of m sub 1 is not equal to 0, then f has a 0 in an interval that is 1/2 of the length of the original interval. And now, we repeat the process by bisecting the new by finding its midpoint m sub 2 interval. Ang bagong interval kay mauna ng a m sub 1 or m sub 2b. Depende sa kung positive ba or negative ang function of m sub 1. Kaya kung ang function of m sub 1 is positive, then we will have the closed interval of an m sub 1. Pero if negative, then kanang isa gamiton nga interval. The process of bisecting new interval will continue until we approximate a 0 in the given function. We continue this process of locating a 0 of f in a shorter and shorter interval indefinitely. And this method of approximating a 0 of a continuous function by a sequence of midpoint is called a bisection method. And for you to understand more, let's have some example to be presented by Judy May.
Zeros of a polynomial function. Example. Show that the polynomial function of f of x equals x to the power of 6 minus 3x minus 1 has a real 0 in the interval -1 and 0 and in between 1 and 2. Approximate the 0 and between 1 and 2 to 2 decimal places. We can observe that if we evaluate the function of x equals -1 to f of -1 is equal to 3, we can observe that our result would be greater than 0. And if we evaluate in 0, you got f of 0 equals -1, wherein the result is less than 0. So this change is telling you that assuming the function is continuous in that interval, the change between negative to positive implies that must pass through 0. So in other words, there is at least 1 0 of f in the interval -1 and 0.
f of x equals x to the power of 6 minus 3x minus 1 with an interval of 1 and 2. With the use of our equation, we're going to substitute 1. So f of 1 equals 1 to the power of 6 minus 3 times 1 minus 1 is equal to negative 3. So we're going to substitute also the 2. So f of 2 equals 2 to the power of 6 minus 3 times 2 minus 1 is equal to 57.
Suppose that our f of x is equal to 0 to our given equation. We will find now our a and b such that f of a is less than 0 and our f of b is greater than 0. So from our problem, we have the interval of 1 and 2 wherein our indicated a here is 1 and our b is 2. So first, we need to find our first approximation to the 0 root using the bisection method or the bisection formula, which is m1 is equal to a plus b. Our first approximation to the 0 with the interval 1 and 2, we will use the bisection formula or m sub 1 equals a plus b over 2. So since we already indicate our a and b, let's substitute everything. So m sub 1 equals 1 plus 2 over 2 equals 1.5. So from our equation x to the power of 6 minus 3x minus 1, let's substitute our result. F of 1.5 equals 1.5 to the power of 6 minus 3 times 1.5 minus 1 is equal to 5.890625, which is greater than 0.
For our second approximation, now our root lies between 1 and 1.5. So our m sub 2 is equal to 1 plus 1.5 all over 2 is equal to 1.25. As you can see in our bottom part, as I already evaluate the equation, we have the result already, which is negative 0.93530273, which is less than 0. For our third approximation, now our root lies between 1.25 and 1.5. So our m sub 3 equals 1.25 plus 1.5 all over 2 is equal to 1.375. So as we can see on our bottom part, we can see the result of our evaluation, which is 1.6329689, which is greater than 0. And our fourth approximation, our root now lies between 1.25 and 1.375. So our m sub 4 equals 1.25 plus 1.375 all over 2 is equal to 1.3125. So at the bottom part, after our substitution, we have the result already wherein it is 0.174559118, which is greater than 0. In our fifth approximation, now our root lies between 1.25 and 1.3125. So our m sub 5 equals 1.25 plus 1.3125 all over 2 is equal to 1.28125. So from our substitution and our bottom part, we have the result already, which is negative 0.4198769, which is less than 0. For our sixth approximation, we have here the root lies between 1.28125 and 1.3125. M sub 6 equals 1.28125 plus 1.3125 all over 2 is equal to 1.296875. So on our bottom part, as we substitute everything, we have the result, which is negative 0.1330164, which is less than 0. In our seventh approximation, our root lies between 1.296875 and 1.3125. So m sub 7 equals 1.296875 plus 1.3125 all over 2 is equal to 1.304685. So at the bottom part, as we finish our substitution, so our result would be 0.0181184, which is greater than 0. For our eighth approximation, now our root lies between 1.296875 and 1.304685. So our m sub 8, gonna add those two terms divided by 2, so our result would be 1.300782125. So at the bottom part, as we finish our substitution, so the result would be negative 0.05810422, which is less than 0.
For better understanding from our topic, we have to find the zero of a function. For this, we have to put the interval in function where we check the answer is greater than 0 or less than. After that, we will find the midpoint of interval. Mautong lies or root lies between 1.25 and 1.5. And we will keep it in place or add those two terms of interval where in previous interval values comes greater than 0 and less than 0 value. So we will continue this process and will reach the desired value and gonna round it off according to instructions. So after our 8 approximation, we find that our m sub 8 is equal to 1.3000781 with an error less than 0.005 or negative 0.0581042, which is less than 0. Hence, we need to round it off to 2 decimal places. We find that our m sub 8 is equal to 1.30, which is an approximation to the 0 with an interval of 1.2 for our f that is accurate to 2 decimal places.